Assalamu alaikum dear students, welcome to the lecture of the nuclear mechanics. In this lecture I will give you brief review of the nuclear terminologies and its concept and various fixed quantities like in this we will discuss about the various mass of proton, mass of neutron, which we need to remember, and it can be asked in any interview or any question, objective questions. The first is mass of proton, which is equal to 1.67 cross 10 power minus 24, and if we convert in the atomic mass units, so it will be 1.007276, and its units in term of electron volt, it will be 938.27 mega electron volt over c square. This is its relativistic mass, and that next in mass of neutron, which is 1.6749 cross 10 power minus 27, and so on, and you can see its relativistic mass. Similarly, mass of electron, its atomic mass units, and then its relativistic mass. And 1 EMU, you know that 1 EMU is equal to 1 mu, which is 1 over 12 of mass of carbon atom, which is 1 over Avogadro number, and is equal to 1.66 cross 10 power minus 27 kg. And usually a number of neutron is represented by n, number of proton is represented by z, which is known as atomic number, and number of nucleon number is just sum of neutron plus protons. Another term is nucleid. What is nucleids? Nucleid is a single nuclear species having specific value of number of neutrons and atomic number, means a single nuclear. For example, if we talk about nitrogen, so it have definitely number of neutron and proton. And isotopes, nucleid having same atomic number but different number of neutrons or different mass number are termed isotopes. Iso means same and topes in place. They are placed in the same. They are in the place in the same space in periodic tables. For example, carbon 12, carbon 14, and similarly these are isotopes. And chlorine 35, chlorine 37. Its mass number are different, but atomic number mean number of proton are same. Similarly, protium, deuterium, and tritium, these three are isotopes. Their mass number are different, 1, 2, 3, and their atomic number are same. Are isotopes of carbon, chlorine, and hydrogen respectively. And the next is isotones. These are those nuclei having same number of neutrons are called isotones. They have different atomic number or atomic mass. For example, tritium and helium 4 and carbon 14 and oxygen. So these have same number of neutron. Neutron can be found, for example, if you subtract this 3 minus 1 means neutron mass number minus atomic number, this will give a number of neutron which will be equal to 2. Similarly, if you subtract this mass number 4 from 2, so it will give 4 minus 2, which is equal to 2. And these two have same number of 2 neutron in this and 2 neutron in this nuclide. Similarly, for these two atoms, you can find the number of neutron by mass number, which is 14 minus 6. It will give us 8. And similarly for this oxygen, 16 minus 8 will give us 8. The number of neutron are same, so these call these nuclei as isotones. Another term for this isobars. Isobar, the nucleids having same mass number but different atomic number are called isobars. For instance, carbon 14, nitrogen 14, these are isobars because their mass number are same but atomic number are different. Similarly, argon and calcium, their mass number are same but atomic number are different. Neutron and proton together are called nucleon. Their mass number are same and atomic number are different. These are called isobar of each other. The second thing is nuclear radius. Nuclear radius can be found R is equal to R naught a power 1 over 3, where R naught is the constant, which is equal to 1.1 Fermi femtometers, and which is equal to 1.1 cross 10 power minus 15 meter, because femto is 10 power minus 15. and we can determine it experimentally by falling alpha particles on a nucleus, and we can find from the distance of nearest approach we can find its radius. So nuclear radius is equal to r is equal to r naught. If we are given with the mass of any atom, so we can find its radius by this hypothetical experimental formula. Note that the nuclear density is independent of mass number. All nuclei have the same nuclear density. We can find the density of any nucleus because density is equal to mass over volume, and volume is 4 over 3 pi r cube. If we put the value of this r at this point, so mass is constant and atomic mass is constant, so this will give fixed density of all the nuclei. So if you are asked and time the nuclear density is independent of mass number, all nuclei have the same nuclear density. The next term is nuclear spin, means if electron is revolving around the nucleus, and it has two types of motion. The first is spinning motion, mean motion around its axis, and the motion around its nucleus. Similarly, this nucleus is also spinning about its axis, which is called nuclear spin. Like electron, proton and neutron are also spin half particle. They can have spin odd half multiple of h cut. The magnitude of spin angular momentum, you can see that S is equal to S into S plus 1 over h cut. S is equal to S into S plus 1 h cut. So if S is 1 over 2 spin, so 1 over 2 into 1 over 2 plus 1 is will give under root 3 over h cut. They, if their spin is half integral multiple, so it means they follow Fermi-Dirac statistics or Pauli exclusion principles. Hence they are called fermions. Means like electronic magnetic moments, the nucleons also show magnetic moments. The unit like Bohr magneton in atom is nuclear magneton. Mean if we have to find the magnetic moments of nucleus, so we will express in the nuclear magneton for nucleus, which is equal to nuclear magneton is equal to E h cut over 2 mp, because in nucleus we have mass proton, so its mass will be mass of proton E h cut over this, and which is equal to 3.15. The z component of the spin, because spin is oriented at some angle with the z axis, so the effective component will be z components, like which is spinning around around its z axis, so its z component will be mu z cos of theta. So we can find its z component, which is equal to 2.7928, and you can see that this z component is less than the whole spin. The neutron has a corresponding magnetic moments, because in the nucleus we have proton and neutron, so nucleon have a magnetic moment which is equal to 1.9130 Bohr magneton. And these, if some particles has magnetic moments, then you can say that this particle is further subdivided, means proton is further subdivided into particle, for example up charge, down charge, and similarly we will see later. And neutron is further divided into further small quarks. So I will stop at this point, and in the next lecture we will discuss it more.